I'm Jimmy Weber, and this is a work that has been done in collaboration with Theo Ballet in the University of Paris-Saclay and Melika Paven, my supervisor at the Institute of Neuroinformatics in Zurich. So I'm going to talk about hardware and software co-design. What does it mean? It means that on one side you have the software, which in our community is usually spiking neural network. And on the other side, you have the hardware, which is usually a neuromorphic chip. Right? So you have this neural network that has a set of weight theta and a loss L. And on the other side, you have this architecture, whatever it is, that has some parameters A, like the configuration. And and at some point you want to design either a chip that's going to be general purpose where you can put whatever neural network on it, or the other way around, you have a neural network and you are designing a specific chip for it. So it's a bit like there are no very good solution. So it's better to find a trade-off where you can have a chip that you know gonna be able to support some of those neural network, but that's not general purpose. Eventually, you have to put this neural network onto your chip, and that is depending on a certain routing algorithm. Why am I saying that? It's because you have to take this network, put it into that chip, and it has to fit into it, right? So on one hand, you have to be sure that there's going to be enough resources on your chip to map this neural network onto it. But also, it's depending on the routing algorithm that you're going to implement or the placement that you're going to do. For instance, if I need to put this neural network with two subpopulations into this neuromorphic chip, I can just put the two populations into two different cores. But if I'm not smart about it, for example, I put a bunch of the green ones in this one and a bunch of the blue one in others, then your neuromorphic chip is not suited anymore for your neural network. So just to say that in a more broadly view or more formal view, you have the spiking neural network where you are trying to minimize the loss. You have you can do choices about the data set you're going to train on, the neural model, the number of neurons, and the connectivity with the weight values. For this talk, I will consider that my data set is fixed, as well as the neural model and the number of neurons, and that we're going to only play with the connectivity of our network. And the objective is obviously to minimize the loss with respect to the degree of freedom that we have, which is the weights. On the other side, we have the neuromorphic chip, where basically you tend to minimize the power, increase performances, and minimize area, so the PPAs. The parameters or the choice that you can do when designing the technology, the architecture, and the routing algorithm that I was telling you about. And finally, you have the specific configuration setup that you're going to have. So it's not because you only have like a multi-core that you initially know the number of cores you're going to have or the fan-in, fan-out you're going to have for each of those cores. And in this talk, I will say that we have a fixed architecture, but we still need to design what we're going to have as the specific configuration of this architecture. As I said, you want to put this spiking neural network onto this hardware, and you want to match the constraints of the hardware. The constraints that I represent by a C is then if you compute the number of constraints that you are potentially violating, or that is like overusage of your chip, this constraint function is a function of the set of weights, so your neural network, the architecture, and the routing you're going to make. And you want this, when you are counting the number of constraints that you are violating, to be below or equal to 0, which means I'm able to put my spiking neural network onto my chip. Finally, we want to reconcile those two. So doing basically minimizing the loss with respect to these constraints. And so we are minimizing the loss with respect to the constraint below 0 and having as a tunable parameters the set of weights and the precise architecture parameters that we're going to have. Again, the A there is, for example, the number of cores. the number of fan-in, everything. Right, I hope you all follow because this is going to be central for the rest of the presentation. So this is the problem we want to optimize. As I said, you have this constraint terms that is counting the number of hardware constraints that you are violating. If this term is below 0, then you are underusing your resources on the chip. If this term is equal to 0, you have a complete usage of your resources on your chip, and you're above 0 over usage, so your network does not map onto your chip. What we usually do when we are training neural network, we are using the gradient descent in backprop. I know there are unsupervised methods, but I'm not going to talk about it today. And the loss is differentiable. The problem is that this constraint term is highly non-differentiable. These constraint terms capture, for example, the number of cores, which is a discrete number. It captures the routing algorithm, which is sometimes solving a whole constraint satisfactory problem that you cannot backpropagate through that, right? So we have an issue here. You cannot just optimize with a non-differentiable term into your equation. So the point of this talk is basically to still do it. How are we going to do it? We're just going to do it in the first part of the talk by tuning, like minimizing with respect to the set of weights. So this is the problem. And before tackling it, I'm gonna rely on your knowledge. If maybe you know the deep R algorithm that was presented by Guillaume Bellec in 2017. For those who doesn't know what deep R is doing, deep R was facing this problem. He wanted to train a neural network with a fixed sparsity, let's say 7 weights in your overall network, and he has no constraint on the connectivity. So he could put his weight wherever he wanted to. The solution he had was dynamical search inside this architecture. So just as an example, let's say you have this neural network. Deep R would first train it a bit. So as you see, those weights are kind of being changed. Then you would select all the weights that are below a certain threshold. You would remove it. And then you would randomly reassign some weights in your network so that you are matching the constraints with being 7 weights. Okay? So this is the deep R. As I said, so if I'm putting some formalism onto that, you'll have the set of weight and the loss. The first step was doing one epoch on the gradient descent with a certain regularizer here, which was ensuring that some weights would go, or all the weights would decrease in amplitude. Then pruning, as I said, so that the number of weights, so this is the L0 norm, saying number of non-zero elements into your weight matrix. So this term to be below 7 while pruning. And then finally, reassigning at random in such a way that we are matching this number. Right. Question is, oh, and sorry, and finally, you'll have to iterate over and over through epochs. So it's a modified step in your epoch in your backpropagation framework. But why is Jimmy telling you all this story for? Does anyone have a hint of what I'm telling you about this story here? I'm telling you then. So the point is that Guillaume didn't know, so the deep R algorithm didn't know that basically they were solving a bigger problem while having this technique. Here you can see that the constraint that they were imposing themselves was having a fixed number of weights, which in this case I set to 7. So they were also kind of, at that time, solving this equation, minimizing a loss while satisfying a constraint. So in the end, we can just take the deep R and make it a bit more general so that we are reconciling this overall formula. So here was the original deep R with a constraint being setting a fixed number of weights. But the extension of deep R would just be we are performing a gradient descent on the loss plus a certain regularizer gamma, then we would create some headroom, which means we would reduce the load that we are putting on our constraints. So we would apply a transformation of our set of weight so that the constraints now is below 0. And then when we have some headroom to do dynamical search, we can apply another transformation in such a way that the constraints now is matching 0. And again, iterate. So we are again modifying our epoch step in our training step inside our backpropagation so that we can minimize the loss with respect to constraints. There are some considerations here. The first one is that we're going to need to compute the constraint here quite a lot of time, right? As I said, it can be basically all the routing part or all the like checking if our spiking neural network would map onto this chip, which can be like whatever algorithm that is time consuming. So, and as we are doing it a lot, we need that this computation should be efficient. The second point is that we need a regularizer here that needs to kind of follow the same direction as our hard constraint. So this regularizer should be a soft version of our constraints that needs to be differentiable. So gamma is a regularizer, a proxy of C, and it's a soft constraint that is differentiable with respect to the set of weight. Okay. I hope you got that, because this is the main part of the talk. Right, now we want to apply that to a specific chip. And at the Institute of Neuroinformatics in Melike's group, we are developing currently a chip that is called Mosaic. And it's not fully designed yet. As I said, we don't know yet what will be the size of the cores or the different configuration of the actual chip. But still, we have an architecture, or an idea of the architecture. So it consists in a neuron tile, which is a population of neurons. And we're going to have several of those populations, several of those neuron tiles that are going to be connected by other router tiles, right? And so that's why it's called Mosaic, because you have a beautiful mosaic here. As I said, the hardware try to minimize or optimize the PPA. You have like you can make choice on the technology, architecture, the routing, and so on. But the overall point is to respect this constraint. In Mosaic, the technology is memory store crossbars. So each of those are memory store crossbars. It consists in a systolic array that you can see here. The routing scheme is Manhattan that I'm going to describe to you in a few, like next slide. And the configuration or the precise setup that we need to define is the size of those different crossbars and the fan-in, fan-out of each of those. So Manhattan, what is Manhattan? Let's say we have to connect those two neurons, those two purple neurons here and there. What we will just do is create a route that goes through those router tile crossbars. We need to create another route, let's say from this red one to this red one. We want to connect the red one to this one, then we can just reuse partially this route at the level of a router or at the level of a neuron. And we are adding more routes there. Eventually, what we are facing is that if I want to connect this neuron to this neuron, then I don't have enough routing resources here. So as I said, we are trying to minimize, we are trying to comply with the constraints. And here, the constraints of Mosaic mappability is basically routing resources. If you remember the summary slides, we want to evaluate the constraint efficiently. But trying to put or to map all a neural network onto this neuromorphic chip is quite computation intensive. So again, instead of solving a mapping for each neural network, we rather want to have a fast approximation of this mappability. And that's very specific to our chip. So if you want to do that for your own chip, you don't have to do what I'm going to describe to you. Eventually, you just have to have the constraints and the gamma, but you don't have to go through all the hassle I'm going to describe to you now. But still, we wanted to do it for Mosaic. And as I said, evaluating the constraint was quite intensive, so we required a fast approximation. Again, this fast approximation should take inspiration from the fact that our bottleneck is the routing resources. So the fast approximation should penalize according to the distances, since a longer route in our Mosaic would consume more resources. How did we do that? We first characterized all the distances between cores. So for example, from neuron tile 0, 1 to neuron tile 1, 2, you have to go through 1, 2, 3 router tiles. So you are using 3 resources. So you can see that from the core 0, 1 to 1, 2, you are using 3 resources. So we did that for the whole different cores. And then we need to, as I said, penalize or regularize according to the distance. So what we did is that for each of those distances, we assigned a specific sparsity. So we imposed first that, for example, all the cores that are only one distance away, that need only one resources to be connected, we impose a sparsity of 50%. All the cores that are 3 resources away, we imposed a sparsity of 20%. And let's say all the other sparsity, we set it to 0%. So then we have this intercore sparsity profile, and we need to create a neural network out of it. So we are just creating a neural network, and we are questioning ourselves, is this constraint that we're imposing of the sparsity a good approximation to match mappability? So I'm just going to rephrase that. We characterized the intercore distances. We impose, according to those distances, a specific sparsity. We create some neural network. We are checking if they are mapping on the chip. We are trying that with maybe the 50% is not good, maybe the 20% is not good, so we are just doing sweeps along those dimensions to check what would fit on the chip. And so here you have like a two-dimension sweep where we are sweeping the intercore distance, the sparsity of intercore distance equal 3 and here equal 1. We are checking whether it maps or not, and depending, as soon as we are over our maximal resources allocation, then we are not mappable anymore. While in this region, we are mappable. Okay. This thing was only for all the blue tiles here, but the bottleneck might arise in another place than in this blue router tiles. It can also happen here or there. So we did this resource utilization for all the different blocks that we had in our Mosaic chip. And then eventually we are able to say, okay, then the P3, so the intercore distance equal to 3, the sparsity between cores that are of distance 3 should be around 14%. And so we are doing the whole sweeps for all the different intercore sparsity, and we found some combinations that are mappable and that are a good approximation for mappability. So we are saying, okay, the combinations of those different sparsity should be p hat. So our constraint is we want all the intercore sparsity to match our p hat. First question was, is this fast approximation of our hard constraints good enough? Yes, it's good, because you can see that even if we are instantiating a lot of different neural network with those specific combination of sparsity, the standard deviation is very low. Here, the hard constraints is based on sparsity being also non-differentiable. So we didn't solve yet the non-differentiability, and we are still, the constraint here is still a hard non-differentiable constraint. And finally, the mappability here depends on the resources that we have on our different elements, right? If I'm having more resources, then my mappability could increase here as well. All right, so we have this first term, the C, that we will be able to plug here. But as you may remember, we also need this gamma, which is a soft constraint. So this guy. So the hard constraint is based on sparsity. Sparsity being the number of non-zero elements, so the L0 norm, divided by the overall number of weight possible. So this guy here is non-differentiable. But what usually people are doing when they are facing a L0 and then they want to make it a soft constraint, they just transform it into a L1 norm. And that's it. So we found, for our specific case, the C and the gamma. And so we were able to train hardware, like routing aware and architecture aware, our Mosaic chip. And so that's what we did. Eventually, we needed to see whether we are changing the resources that we have on our chip, whether it will increase the accuracy or not. So we just sweep on the A values. So we increase the number of resources that we had on our chip. And here would be a kind of expected results, right, regarding the loss. Or if I replot that in terms of accuracy, you're expecting that if I put more resource on my chip, then I have a better accuracy. So it's not only visuals, it's actually implemented. And so our results are those. Regarding the test accuracy and the number of memory counts, so the resources that we are having on our chip, you see that having more resources increase accuracy. Here, those dots are the baseline. The baseline meaning if we were not to do a dynamical search of our architecture and just imposing a fixed weight matrix and just training on this one for the whole time. So you can see that we gain 5%. And another interesting outlook, so further insights and outlook, is that when sweeping around the two dimensions, so P3 and P1, which are basically characterizing your hardware, we observe that the standard deviations of the accuracy were quite low, which kind of indicate that a family of hardware have the same accuracy, but also it indicates that if you have populations that are of different distances apart, right, and you are constraining the sparsity of those different populations, then only the sparsity would determine the accuracy. And the accuracy is basically a function of this interpopulation sparsity. At least that's what we observed in our Mosaic chip. Finally, here is the take-home message. So here was the title, Hardware Architecture and Routing Aware. So we did hardware architecture and routing because we were able to characterize our constraints through this function, the C. We did aware training since we developed this inspired by deep R method where we are minimizing the loss, respecting those constraints. We did optimally memory usage because we try to have a C at the end of our training equal to 0. And finally, the case study was the Mosaic architecture I described to you. And finally, we're able to have this nice plot where we could basically make the trade-off between resources that we want to have on our chip and accuracy. And with that, I want to acknowledge the whole ICE lab from INI that's in our retreat, Theo, whom I worked with, and Melika, my grade supervisor. Thanks a lot.